I just started a screencast in case anyone ever wants to watch this. All right, so the topic today is that we'll talk about how to use Sage to do algebraic number theory. You can see that I prepared an eloquent lecture on how to use Sage for algebraic number theory. But I did actually give a couple of lectures on Sage and algebraic number theory, which are included in Sage. So the website I just went to is nt.sagenb.org. That stands for Number Theory SageNB.org. It's a Sage notebook server that's devoted to number theory that's hosted here. And you might want to sign into it or get an account on it. It's nice because you don't have to worry about installing Sage on your own computer or anything. Specifically here, though, if you have big computing tasks, we have, so I guess I have like a lot of computers. I don't know, I lost track. I probably have about 15 serious servers downstairs, and each one's pretty powerful. So I'll show you you can get an account on all of these machines if you want as a student here. And I'll just give you an example of one of the most powerful of the machines. So here's a machine called Combinat, which we recently purchased. It has 192 gigabytes of addressable RAM. It actually has 256 gigabytes of RAM, but some of it's used redundantly so that if some of the RAM gets corrupted, it still doesn't corrupt the memory. 64 cores. So it's pretty powerful. If you log in and type top, you have to make the screen really small, but if you type 1, still not small enough, you can see the state of all the processors. There it is. So these are each of the cores. So it's a very powerful computer if you want to do a lot of things in parallel. You can't use it directly through the Sage Notebook by just getting a Sage Notebook account, but you can log into it, start a Sage Notebook server running there, and then use your web browser to work with it. So it's a little bit involved how you do that from any location, but I'll show you what you do. Remember this. So if you have a console on a computer somewhere, so on OS 10, then you type the following SSH-L. You choose some port like maybe 8000, just make up a number, localhost 8389, Combinat Math Washington edu. This only works if you have an account on that computer, but again, if you get an account on that computer, then you can do this. If you're using Windows, then what you would do is set up port forwarding and forward port 8389, and you would do that using just the graphical interface. I think for PuTTY, there's an option to do port forwarding. So this is the command line way of doing port forwarding over SSH. So I log into the machine. Once I've done that, what it does is make it so that port 8389 on Combinat appears as port 8389 on my laptop. So I think this is the right option to run the notebook serving on that port. Yeah. So now I can go with my laptop. I can go to the address localhost :8389, and boom, I have my own personal Sage Notebook server running there. And the first time I do this, it would ask me for a password, which I don't know what I chose. So if you get in that situation, you can do, let's see, Sage Notebook port equals 8389, and reset equals true, or reset the password. Okay. So now I can go back. And let me, this is a pretty important command I typed right here, so I'll write it on the board so you can remember it. There's 2 commands I've typed total so far, which are really useful to know about in general. One thing is you need to choose a port number that's big and that nobody else has chosen the same computer, otherwise it won't work. And then the machine. So that's one command I typed, and the other one was within Sage. I typed notebook, and then I specified a specific port. And I also said, please reset the password. And I had to type the password for the admin user. So this will give me a notebook that only I can use, or anybody else who happens to be logged into my laptop, which should be nobody in the world. And The password is whatever you set it to be there. The username is admin. And all the files are stored in your home directory. Any data that you create is stored in $home. Oops, it should be uppercase. $home /.sage/sage underscore notebook .sage.nv. So that's where the worksheets are actually stored behind the scenes on the computer that you logged into. It's also secure in that when you connect and type in your password, it's being sent over SSH, so you're not going to easily be giving away your password by doing this.
Is that slash? Did you write slash dot sage on my glasses?
Yes, that's a /.sage. So that's what, you don't really need to know this, but I just wanted you to know. That's where the files are stored. Okay, so at this point, I've now reset my password. I can then go over to here and log in. And it should work. And there it is. So, and now I'll make a new worksheet, which I'll actually use for today. And just to test that I did things right, if you do %sh, you can execute an arbitrary command in the shell. And then notice it says combinat, which indicates that I really did log into this computer, which is nice. There are a lot of advantages to running Sage this way, rather than just using one of the random public servers. You don't have to compete with other people for resources. You can get access to more powerful computers. You can leave a calculation running for days on end. So I could just start something in this worksheet running, kill my browser, go home, type this command again from somewhere, possibly if the SSH connection dies, which it probably would, and then open my browser again, and the calculation would still be running. I can see what had been output. So that's kind of nice. So it gives you a lot of control. But if you're just doing some quick one-off thing, then just using one of the public servers is fine. Okay, I mentioned that there's some information about using algebraic number theory in Sage. So there's something called thematic tutorials. They're available as follows. So I'll just do what I did again. From within the notebook, you click on Help in the upper right. You just click there and you'll see all the help for Sage. And then there's something called thematic tutorials. These are tutorials that are in-depth about specific topics like combinatorics or number theory or something like that. And I think that one of them, well, that's annoying. Okay, I thought I had one in here. That's really stupid. Apparently I don't. It's listed somewhere else. I guess none of these are really interesting for algebraic number theory.
If you do a Google search for number,
yeah.
you'll pull up the one that you're looking for. I think if you want,
well,
about the one for the homework we just turned in.
I know it's in the. I'm looking for the tutorial that is certainly on the Sage Math website called 3 lectures. So library, or I guess support, help and documentation. Okay, I guess, oh, here it is. Explicit methods in number theory. That's not what I called it. That's what it is though. Okay, well, and it is, where, Doc Bordeaux. Okay, well, okay, so let me tell you how I found that. So another place that you can find documentation for Sage is on the Sage website. Let me not full screen this so you can see the URL. So the Sage website, sagemath.org, if you want support, then there's help and documentation under support. And in there, there's lots of different things. And one of them is explicit methods in number theory. Okay, so that's the document that I pulled up. And if you look at that document, it has, basically this was the result of 3 lectures I gave to a bunch of grad students in Europe about using number theory functionality in Sage. And the number field section would be a good one to look at for this course. So here it is. And if you click there, then you get, you can see the contents. And there's a lot of subtleties about, say, using square root. If you want to define a number field, you can do things like q adjoins square root of 2. You can make a number field defined by a polynomial, etc. So there's different ways of defining a number field, and that's discussed And then there's just a lot of stuff about Galois groups. That's not so much algebraic number theory, but just Galois theory. But then class groups is number theory. And then relative extensions and orders. That's what's described here. So that would be a good thing to look through if you wanted to look in detail. This is complementary to the reference manual. The reference manual, I'm sure Ali must have showed you that there's a chapter about, there should be a chapter about number fields, algebraic number fields, yeah, right here. This is in the Sage reference manual. And this systematically documents all of the sort of core number theory function, or core algebraic number theory functionality directly related to number fields. So basically, it shows you how to do things like, given a number field, compute a basis for the maximal order, compute the class group, compute the unit group, find primes of bounded degree, et cetera, et cetera. So this is where the documentation is. Okay, so with that said, what do you want to know how to do? Do you want to know how to do something more advanced than 2 plus 2? The sweet sound of impact drivers. Drills. Didn't help. It's exactly the sound I'm going to hear all afternoon building the skateboard ramp I'm working on. Okay, so what do you want to know how to do? Yes, what's your name again?
Elise.
Elise, yes.
I was able to do it in the homework in kind of a different way, but
Mhm.
if I just want to construct the ring Z adjoins square root of -5, how do I do that? Because I couldn't figure out how to do anything other than number fields, so
Right.
I went that way.
So the question is how to construct in Sage Z adjoins square root of -5?
Yeah, and just any,
That
just
ring.
adjoin anything really.
Okay, let's start with this one. I think one way to do it is to, so ZZ is the integers, and then ZZ square bracket, and then square root of 5, whoops, sorry, ZZ is the integers, square root of -5 is square root of -5, and then you can do Z square root of -5, like that. Thanks to Robert Bradshaw, you can do that, you can use that notation. What it does behind the scenes is it finds the minimal polynomial of that expression that you give right here, if it has, I mean, if it's actually algebraic. So you can give anything that you could represent in terms of radicals and so on. So you could have given a cube root or a 10th power or a 10th root or whatever here, some complicated expression. Then it uses, it'll find a decimal approximation to the number, or at least an interval that the number lives in. I think it finds a decimal approximation to the number, I think. And then uses that to figure out the best polynomial that it satisfies to that precision. Then I think it plugs that number back into that polynomial to check that it really does satisfy it, and then probably verifies that using interval arithmetic. No, it does a ridiculous amount of stuff to efficiently find the minimal polynomial of that thing. Then it constructs the corresponding number field, and then inside of the number field it makes the order, and it does all that kind of automatically behind the scenes for you.
It can't be that good though. I mean, if you throw like a transcendental number in there, is it going to come back saying it's an algebraic?
No,
Okay.
definitely not going to say it's algebraic. I think it'll just give an error. Or, well, I guess it's constructing something else. So a univariate polynomial ring where the variable is called pi. That's actually pretty sensible. So it's one indeterminate called pi.
Well, how does it determine whether something's algebraic or transcendental?
So it uses the triple L algorithm, which is a chapter I skipped in the book, to find a highly likely candidate polynomial that the element should satisfy.
Oh.
And with pi, it would fail at some point. I don't know when it gives up or why it gives up, but I think it just, for certain elements, it can't find a good relation that it satisfies, so it just gives up and decides it's not algebraic.
I thought there was no way of telling for sure, right?
Well, I'm sure there must be some sorts of inputs where it won't be able to decide. Let's see.
Is there a shortcut? Because I had it couldn't be transcendental, so I mean.
Okay,
surely you
that's
could
just an
start
error.
with
Let's see, what's something which is hard? Harder. Sine of 1, okay. I see. I think it's, let's see. So, I mean, it's really using I plus E. I think it's, so it's trying to prove that it satisfies an algebraic relation. It fails, and then it just tries to turn it into, apparently it looks like it's just trying to turn it into, it takes the expression, and if the expression is simply a single variable, a single name, and it can't show that it's algebraic, then it just makes the polynomial ring in that one variable. So that's what it's doing. So it's giving an error here because I plus E, there's no like natural name for it as a single variable. That's what that means. Whereas pi, okay, you can just call it pi. So, like, if you want to see the code, I mean, you don't have. One thing with Sage is you don't have to just idly speculate about how it does things. There's nothing. There's not a single line anywhere in Sage that isn't open source and available to you to look at. So if you really want to know how things work, it's possible. In this case, so the min poly command is sort of what's being used behind the scenes. Min poly on a symbolic expression, which is what f is. And if you're curious how a function works, you can do double question mark after it, and that will look up the source code of that function. Which of course could call other things, at which point you need to start looking at files, and you may have to work a little harder. And that's what happens here. So it looks like it calls a function called min poly. So we'll have to look at that function. And there's not a hyperlink that lets you just click to get into this function, unfortunately. That would be pretty hard to implement, but we can do that at least. So let's see, here's the min poly function, which the documentation doesn't work because there's a traceback that tricks it, apparently. That sucks. Right, the documentation doesn't work. So what can I do? One thing is there's a way to browse the files. So you can do search underscore src and then type something into Sage, and it'll give you a bunch of hyperlinks to the original source code of every file in the Sage library that contains that word. In particular, this function calculus, or this file calculus.py is right here. And so we can browse it with syntax highlighting, find this min poly function. So there's a lot, the docstring fortunately has a discussion of the algorithm, which is probably what you want to read. So there's some numerical algorithm and then an algebraic algorithm, and looks like it does things involving cyclotomic fields. It's pretty sophisticated, but the main numerical algorithm that's used finds a numerical approximation and uses what's called algebra, which is really the triple L algorithm, which is really a generalization of continued fractions to a higher degree. Yes?
On that trace back, you can just click to the left and it's
Oh, within the help message? Okay, good. All right. I'll just leave it. But anyways, here's the source code in the documentation, and you can see it's not so simple. So there's some heuristics. It goes up to some bound by default. So this is something you could override if you want, but I think it goes up to 1,000 bits of precision, and if it fails to find an algebraic relation with a given degree and bit precision bounds, it'll just give up. And that's why it's giving up on things like pi, probably, or at least with completely arbitrary things, it's going to give up. Unless there's some other reason it would know. If you put in something really weird and complicated, and it just, and it is transcendental, what this is going to do is try to see whether it's algebraic using up to 1,000 bits of precision at degree 24. If it isn't, it's just going to give up and just not be able to find it. If you don't like that, you can change the parameters that it uses. Okay? So you can see how looking at the source code reveals that there's more to it than you might think. In any case, it goes through, it tries to approximate to higher and higher precision, etc., etc. So, anyways, that's the source code. And that is probably helpful. Okay. So that's how you can construct z adjoining square root of -5, and many, many other orders. and rings and so on. And you could also do something like this. It'll give you the order generated by square root 5. And you can then ask for the maximal order. Or maybe ring of integers. R dot maximal order. If that doesn't work, I might have to say R dot number field and then ask for the maximal order. Yeah, so R dot number field, that gives the field in which R is contained. And then then K dot maximal order will give you the maximal order, which is a little bit bigger. It's hard to see on my screen if I don't shrink it. Actually, you can't. It's just formally the maximal order as far as it's printed here, but once you have the maximal order, you can ask for its basis. You can see here that it's a little bit bigger than R. So this works fine as a way to construct number fields and rings of integers and so on when your number field is a radical extension of the rationals. And also, I guess, for cyclotomic extensions, which are also radical extensions. So, let's see, what else? Oh, there's an analog of this. You can also do Q adjoin. If you wanted to directly get at that field, you can go QQ square root of 5. And you get the number field immediately. Okay? I think so. Yeah, so this constructs a relative extension. So I think it made the field Q adjoin root 5 over the field Q adjoin root 7. So if we were to say like L equals this, then there's L dot base field, and that base field is Q adjoin square root of 7. So you can do that. I think you could also go Q square root of 5 square root of 7 and build it up one step at a time.
Is there a simple expression? Sorry.
Go ahead.
Is there a simple expression for cubic root and generally?
Yes. So if you wanted to join cube root of 2, you could do this. You go caret symbol and then nothing like that. Or you can use star star. Right? In Python, you have to use 2 asterisks for exponentiation, but in Sage, you can also do caret. Yeah, if you watch out, because like Python can be really annoying. If in straight Python you do 2 caret 1 3, you probably won't get what you expect. So the 1/3 gets turned into 0 because in Python integer division is for division, and then the symbol like that means exclusive OR, and 0 exclusive OR to 2 is 2 again. So it's pretty dangerous. So watch out if you're using Python in addition to Sage. Sage has a language of its own that gets compiled down to Python. So the way you can see what it gets compiled to is you go 2 to the 1/3. If you do pre-parse of 2 to the 1/3, that shows you what the corresponding Python code is. So it turns all the carets into star stars and so on. And it basically operates on single lines. By the way, if you program in JavaScript at all, then there's something called CoffeeScript, which is almost exactly the same sort of thing where you take code. Basically, you can write JavaScript code, but where things are a little nicer than what you would have to write in JavaScript, and it converts it almost line by line into JavaScript. So the Sage preparser is a very, very similar idea to what CoffeeScript is. Okay. That said, of course, there are extensions of the rational numbers that aren't radical, and you also need to be able to construct such number fields. And let's see. So there's a solve command, by the way. So if I do solve x cubed plus x plus 1 equals 0 for x, Sage uses Cardano's formula and finds the roots of that cubic. So more generally, we could try a higher degree polynomial. I'm trying to find a polynomial where there's a root that's not expressible in terms of radicals. So I guess this one's okay. Obviously, it's expressible in terms of radicals. It's the fifth root of minus 2. And you see it written out explicitly. But what if I randomly mess around with this? Still radicals. There. So what this means is that Sage's algorithm for finding explicitly the roots of a polynomial in terms of calculus type expressions fails, and in this case this extension wouldn't be radical. So to construct this number field, what you do is you do number field x to the fifth plus x to the fourth, and this is what you surely already know how to do, plus 2. And you give it a name, and that gives you this number field. And again, you can do things like k dot maximal order, that gives you O sub k. And then OK dot basis will give you an explicit basis for the ring of integers of that field. And just illustrating things we've learned, so OK dot, I think, factor. Oh, it's actually k dot factor, apparently. You can give it a number, and it will factor it, the ideal it generates in the ring of integers. You can also construct the ideal generated by OK times 17. So that's an explicit ideal, and you can factor it. Now it factors it as a product of primes. You can invert the ideal, like 1 over I, call it ideal j, and you can factor that. The result of the factorization anywhere in Sage is a formal object called a factorization. It's a class called factorization. And it works just like a list of pairs, prime exponent, and it also has an attribute which gives you the unit. So if I just call this f, then the type of f is factorization, and you can turn it into a list if you want. And you see it's a list of pairs of prime ideal and an exponent, prime ideal and an exponent. And you can get at the entries, like you can do f. If you do f0, then it gives you back the first pair, the first prime and the first exponent. Okay. You can also do things like ask for the class number of this field. Turns out it's class number 1. That means every ideal should be principal. And notice the ones we've seen are principal. That also means we should be able to factor elements of the field. I think that's true. I think you just do like, here's a random element, a cubed minus a. I think I could just do factor of the element, and it factors it as a product of irreducible elements in the field times a unit. And behind the scenes, what I did was it took the ideal generated by a cubed minus a, factored that ideal, and then took generators for each of the ideals appearing in the factorization, multiplied those generators together, and with appropriate exponents, and had to get something that differs from this by a unit, so then it just throws the unit back in. It figures out what the unit is, and we are. So, okay, next question.
How do you construct finite field?
Okay, so there are, let's see, in a way I guess there are kind of 3 different ways you could get finite fields. So there's a GF command, which stands for Galois field, which is also what you get from finite field. There's, so that's one way you can get finite fields. You can make the integers modulo n, which are not, when n is a prime, they are a finite field. They're not the same identical thing to GFP, but they're canonically isomorphic to GFP. And you can also construct residue fields, so residue class fields. So the situation there is that you have an ideal that's prime in the ring of integers, and you can ask for the residue field. And it really is, it remembers that extra structure of being the residue field. So there's a lift where you can take elements of the residue field and lift them up to the ring of integers and so on. So these are the 3 different situations in which you can make finite fields. So I'll illustrate them. For finite prime fields, it's pretty straightforward because you don't have to explicitly give a generator or anything. You just give a prime number. Even then, though, there is a subtlety. I'll call it k again. So GF of a prime number gives you the finite field of that order. I think the one subtlety is if you're a cryptographer, you could easily end up wanting to specify a prime number which is so large that verifying that it's actually a prime number would take a noticeable amount of time. And you want it Sage shouldn't just blindly try to compute with GF6, so it does check to see whether or not the element is the number is prime. So there is an option where you can tell it to not check, and that's important if what if you're making thousands of these fields, or if your prime has thousands of digits or something like that. Also, one thing to worry about is by default, Sage is always doing things provably correctly. It doesn't say it's happy if the thing just looks like it might be prime due to primality tests passing. So it will prove that the thing is prime before going on with calculations, unless you tell it not to. Yes?
If you want to avoid primality testing, couldn't you also use integers and not?
Well, you'd think you could, but I think it'll check to see whether or not the modulus is. It'll probably check to see whether the modulus is prime due to the optimizations and special features that might be available. So I'm not sure. But the second you try to use it, I mean, if you're making it as a field, you probably want to use it to do something like linear algebra or something else. And so is field will get called on the object, and if you made it z mod nz, it'll end up factoring anyways or doing primality testing. But you can make g of p for very large p and specify an option. So let me show you. It's in the doc string, I think. I remember people who do cryptography complaining about this. So we added it. I added it. The proof thing. So it's such like a simple thing you'd think, I don't know, it was a headache to add this and get it right and so on. People were very annoyed by it not being there. So the default is it proves the number's prime. It turns out that you can prove that numbers are prime in polynomial time these days, but still it's pretty slow. In contrast, if you just want to know that a number is very likely to be prime, then you can do that quite quickly. And the very likely is, I mean, it's really likely. It's like you can, it takes very little time to know that the probability that your number's prime is, 1.000 with 1,000 digits after it. So you can then estimate the probability that bits were flipped on your computer due to cosmic radiation and compare it to. If you were worried about whether you should trust the result. So people do, I mean, it's a good idea to trust probabilistic output, but in Sage, the default across the board is always proving things are correct. That is running an algorithm that, in theory at least, should be proving that result is correct. Fortunately, it's very easy to change that default. All you have to do is there's an object called proof, and it has a couple of different areas of math. So you can do, for example, proof.numberField false, proof.all false, proof.linear algebra false, etc. And what that will do is make it so that calculations are not proved correct by default. Proof.numberField false can make a dramatic difference in the time for certain things to compute. For example, let's see. So right now, I'll try to illustrate this. So right now it's true. Let's make a quadratic field. I don't know how big I have to make it, but okay, so it took a half second to compute that class group. I'm guessing it may be faster if I turn off proving correctness. Let's see. I have to watch out though because it's possible it's caching the calculation. So I'll make it be a slightly different one, and hopefully that isn't going to impact the running time. It might actually, so. Well, I don't know if that convinces you of anything, but let me just try. Let's try exactly the same thing, but in another session, just to see what happens. So, to see whether it looks like 0 or the bigger value. Oh, your sure is working hard. QuickTime player off, recording this talk. Huh. Okay. So then, yeah. So notice that the difference between proof false and proof true is extreme in this example. Proof true, it took a half second. Proof false, it took no measurable time. at least in terms of hundredths of a second. So it's good to be aware of the impact. So I think that in algebraic number theory, this course, of all areas of computation I've ever seen, it probably has the biggest discrepancy in runtime when you basically, if you don't try to prove results are correct using using theorems, then you can do things dramatically faster in algebraic number theory than if you do. And the difference is really, really extreme. So you want to watch out for that because you'll undoubtedly run into it in here. The reason for that, I mean, there's a lot of reasons, but one of the nuisances, believe it or not, is that nobody's proved the Riemann hypothesis or its generalizations to arbitrary number fields. And it turns out that if the Riemann hypothesis is true, then there are, bizarrely enough, there are many algorithms that are suddenly provably correct and have really good complexity. Basically, there are lots of algorithms that involve doing things like look at all the prime ideals up to a given, with norm up to a given bound. And that bound, if you don't know the Riemann hypothesis, is way the hell up there, whereas if you do know the Riemann hypothesis, it's really small. So in practice, people have conjectures that are even stronger than the Riemann hypothesis that give even better bounds, which they're pretty confident of. So there is that sort of problem. But most of basically if the Riemann hypothesis was sort of proved, then these times would all be a lot smaller. So another thing to watch out for, so there are other computer algebra systems out there like Paris, which Sage uses. Paris, by default, never proves anything. Basically every answer it outputs is likely to be sort of true with high probability, but not proven. So in the sense that you're using an algorithm where it should be right and it should fail almost 1/2 to the 100th of the time or something ridiculously small, but it still isn't rigorous. So you have to watch out, especially if you benchmark Sage versus one of these other systems. So you benchmark maybe Sage versus Paris for this calculation, and you might think, oh my god, Paris is 1,000 times faster. But in fact, Sage is just using Paris to do this with different options. Sage, when we wrote this, I looked very carefully at the reference manual for Paris and figured out how to get it to prove correctness of the result and do that by default. So that's the discrepancy here. And there's similar remarks with Magma, where Magma, generally speaking, tries to prove things are correct, but it will sometimes it doesn't, and so you have to watch out there, because it may seem really fast, but actually not be provably correct. Okay, so that's my little spiel about provable correctness in Sage. I'm not sure that we made the right choice by having provable correctness by default always be on, but that's the way we did it, basically via vote. So I guess mathematicians are voting, so. And again, it's easy to, as long as you're aware of this, which you all now are, you just do proof, just type proof.tab and you see the options, and you can easily turn this off. And it can be a good idea to do that first time through if you're writing a paper, and then you could rerun the same code and prove true, and make sure you get the same answers. Okay. All right, so next question. Oh, I didn't tell you very much about how to make finite fields, did I? I don't feel like I fully answered the question.
I want to know how do you compute an order of an element in the group?
Okay, that's a good question. So here's a finite field sitting up here. This is how you make a finite field with bigger cardinality. And now you might ask, oh, every non-zero element of this has some multiplicative order. So how do you compute its order? How do you get at that underlying multiplicative group? So I'll tell you that in a second. By the way, you can specify, so finite fields, they'll come up with their own defining polynomial. You just give the order of the field and it chooses a defining polynomial. If the order is small, it will use a Conway polynomial, which is supposed to be good for some reason. And if the order is big, it'll just find some polynomial. But you can also specify your own polynomial if you want. Behind the scenes, Sage's finite fields are implemented using a combination of new code that we wrote, code that's in Paris, code that's in NTL, and code that's in a library called Givaro, Givaro. So there are a whole bunch of different potential underlying C or Cython or Python libraries that are implementing the arithmetic in finite fields. The net result of this is that you can run into bizarre things where you make a finite field of order slightly smaller than 2 to the 16, and it's insanely fast to do arithmetic, like faster than any other program in the world. And then you make the order slightly bigger, and it suddenly becomes quite slow. And that can happen due to switching over from Chavarro to Paris, for example, for the underlying representation. So watch out for that sort of thing as well. And the cutoff points are different than Magma, for example, where Magma uses a different collection of code for different types of finite fields. So it might be really fast up to a different bound. So there is that to worry about. In any case, your question, let's get a random element of k. Hopefully it isn't 0. Nope. I think we can just do multiplicative order. Boom. So that is the multiplicative order. And it seems plausible because the field is order 256, and a lot of elements of order 255. So it turns out that one is a generator. I think that by default, I think when it gives you back this A is a generator for the field as a GF2 algebra, so as an algebra over its base field, when possible, which is possible here. I think it also tries to make it a generator of the multiplicative group, but I don't know if that's guaranteed in general. Here it is, in fact, a generator. Okay, so yeah, let me show you residue class fields, because you might not know about that otherwise. So if I make a number field like, actually I'll make a z adjoin square root of minus 5 again. And then I'll make number field. So I got the field that contains it, and then I could do k dot factor 7. So that's going to give me product. So I'll take one of these primes, and then I can do p dot residue field. Kind of a boring one because it's going to have prime order, but that gives me the residue field. So it's the quotient by this ideal of the ring of integers. And it has a cardinality, which is 7. If I take an element in there, I can lift it. That is extremely unimpressive because it's let me try to find a prime where it's not so boring. Yeah, that's a better one. Okay, here's one where the residue class field. What? No, lift. Maybe it's the other way around. Yes, okay. Okay, so what I've done here is I changed my mind. I took this field, now I took the prime ideal generated by 11, factored it. Turns out it's still prime. So I took 11 times the ring of integers, that ideal. I took the residue field, which is not a prime field. It's not of order 11, it's of order 121. And then I took a random element, and now I'm going to lift that random element back up. Okay, so that gives me something that reduces to that element. So you can see that it's remembering the structure. You can also take an element of the number field, like square root of minus 5, so that would be k dot 0, I guess, the generator of k, and you can map it down. So that tells you where things go. So basically what's happening here is we're working with OK, and then also, well, we explicitly have a map from OK to OK, modulo the ideal generated by 11. Right there. And so this is the residue field. This is a finite field. And the code in Sage that you can work with finite fields represented this way was written by David Rowe. He hasn't been doing much on Sage lately because he's very busy teaching a computational number theory course. So it might be worth checking to see if he has any notes online about that. If you're interested in computational number theory. Okay, so that's more about finite fields. And so notice the key thing was multiplicative order. I think if you just tried, like here you can also do multiplicative order for your original question. But if you were to just try order, you get a sort of an error message. The problem is that the word order is pretty ambiguous in mathematics. So you take an element in a field, which order are you talking about, the additive order or the multiplicative order? And you could easily want either one. And so we decided to deprecate order being the additive order and make it so you have to explicitly say additive order or multiplicative order. And that's what this error message is about. By the way, arithmetic is very fast for small finite fields due to use of Javaro. So this benchmarks multiplying beta by itself. It's taking 256 nanoseconds per arithmetic operation, which is really fast, actually. I don't know if you have a good feeling for nanoseconds, but that's pretty good. It's a fourth of a microsecond, which is way less than a millisecond. So it's like a 4,000th of a millisecond. So it's like a 4 millionth of a second. So that's good. That's what you want your arithmetic to be like. Okay. All right, next question. We have time for one more question.
If you have a number field, how do you add it into real numbers or
That is a good question. They're all such good questions. So let's see, we have a number field, K, and there's a method on it called embeddings. And basically you can give as input to that method any field, and it will find all the maps from K into that field as maps, as morphisms. So we'll find all the maps into R. It'll be pretty easy. There aren't any, because it's 3 times square root of minus 5. But we can also find the maps into CC, which is by default 53-bit double precision complex numbers. And you see that there are two maps. One of them sends square root of minus 5 to this, and the other one sends it to that. Okay? You could also find, and these are actual morphisms, so if you say v equals this, then you can do like v0, and you can apply it to an element, like that. It'll unwind the element, apply the map, and give you back something. You can also do k.embeddings. You could make the complex field with, say, precision 200, and it will give you all the embeddings in the field with larger precision, as you can see. You could also ask for the embeddings of k into itself. And there are two of them. These are the automorphisms of a field, as a field over Q, as you can see. And if the cardinality of the number of embeddings of k into itself is equal to the degree of k, that's the same as k being a Galois extension. But it may or may not be the case. So if that answers your question.
And can you find also a subfield of R that forces as an multiplicator?
Yeah, subfield of R is C.
So if
No.
embedding, can you find it?
No, I don't think so. Because there's no data structure in Sage that represents, or maybe you can. Actually, there is a way to equip a number field with an embedding. So this K, I think, actually has a canonical choice of embedding into C because it was constructed as by adjoining square root of minus 5. So I think that means that if you do a coercion like this, maybe not. There is a way, when you define a number field, you can equip it with a fixed choice of embedding into C. And then, in a sense, that's like making it, or viewing it as a subfield of C. But I'm not sure immediately off the top of my head how to do that. Okay, so I think we're out of time. So that's it. But we'll talk more about Sage at some point in the future. I remember we're going to start with